This is day 6, or video 6 for chapter 2. That still is awful long, especially if you get ones down at the bottom. And so I've picked some elements from down at the bottom where we're going to do a shortened version. So for the noble gas configuration, we use the noble gases on the very far side to shorten the configuration. So the first one is hafnium, and hafnium is down this column right here. We use the noble gases, which are on this column, and say hafnium is like xenon. So everything up to xenon is the same. So we put xenon in brackets to say it's like xenon. And then we just start from right there. So then we'd come over here to the 6, and we go 6s2, and then go through that to here, 5d2. The only thing that we have to do by noble gas configuration is we have to rearrange it shells so that the smallest shell is closest to the noble gas and the biggest shell is away from them. So this becomes xenon 5d2 6s2. Okay, let's do praseodymium. Praseodymium is down, oh, you know what I forgot? I forgot the F. And that's what this little section here, we forgot to go down and then come back up. So let me fix this because this is a common mistake. So we should have gone down to the 4F, gone through 14, and back up to the 5D and done 2. So then when we rearrange it, becomes XE 4F14 5D 2 6S2. There, much better. Okay, so then we go to praseodymium. Praseodymium comes off that same row, so it's also going to be xenon to start with. And it's going to have 6s2, and then it's going to down to the 4f, and we're going to go through 3. Rearranging that, xenon, 4f3, 6s2. Don't try and shortcut it by rearranging it to start with, because I find when kids do that, they actually mess up even bigger, and that's not a good thing. So let's go on to lead. Lead is right here. Okay, so again, xenon. I must have been on a xenon kick, I guess. So you start with xenon, come back over to 6s2, down to 4f, 14, back up to 5d10, and then over to 6p2. So when I rearrange this one, it's going to have the 4f14, 5d10, 6s2, and 6p2. Okay, see if you can do tungsten and seaborgium on your own and then bring it back to the video. So go ahead and pause the video. All right, coming back for this one. Tungsten, same thing as xenon. Like I said, I must have been on a xenon kick. And it is the 6s2, 4f14, that's lovely 4, 5d, and that one's in 4. So rearranging, xenon, 4f14, 5d4, and 6s2. For seaborgium, seaborgium is actually down one. Yes, we get to use radon. And then we're going to come over and use 7s2. And then we go down to the 5f14, back up to the 6d, and we're into it 4. So rearranging here, radon, 5f14, 6d4, and 7s2. All right. So the valence shell electrons are our outer shells. Whoa, that went really fast. Let's see if we can go back here. Our outer shells, our outer S and P. So the highest number with the S and P. Okay, so for beryllium here, we have valence shell number of 2. That's the highest number in front of an S or P. The number of valence electrons is the S and P added together. So here there's no P, so it's just 2. Over here, the valence shell is 3, but we would add this plus this to get the number of valence shell electrons. And valence shell just means it's the outermost shell. And they become very important because those are the ones that are going to be used to react with other elements. So it's really easy when you're looking at the periodic table. First column has 1 valence shell, second column 2 valence shell. That D area, that sunken area, and the F, they have 2 valence electrons, but some of them still to complete and only have 1, and so they're sort of funky, but for the most part they have 2. Then we have boron's column has 3, carbon's column has 4, nitrogen's column 5, oxygen's column 6, fluorine's column 7, and the noble gases for the most part 8, but remember that helium only has 2 electrons, so it only has 2 valence electrons. And that's why in the families, those are the columns on the periodic table, they have similar reactivities to different chemicals. So if you're looking at the actual last shell of all of these on the electron configuration, you can see that the S is the same right here, or the P is the same right here, or right here, so that they'll have the same amount in their outer shell. Okay, so we can also do, when we're putting chemicals together, we need to be able to how they do spatially. And so we do what's called an electron dot, or Lewis dot is what you'll hear me call it. And the dots represent those outer shell electrons. So each dot represents 1 valence shell electron. So hydrogen would have 1, carbon 4, oxygen 6, chlorine 7. So let's take some and figure them out. So hydrogen has 1 valence shell electron. It should have 1 dot. We usually start at the top. This one up here did it to the side, but we usually start on the top. Sometimes they put it on the side when they're doing formatting in textbooks. So carbon has 4, so we start at the top and we put 1, 2, 3, 4 dots. Oxygen has 6, so we go 1, 2, 3, 4, 5, 6. Chlorine, 7. 1, 2, 3, 4, 5, 6, 7. And then beryllium has 2. Now, electrons don't like each other, right? So they want to be as far away as possible. So when we do something that has less than 4, we do it as far as possible. So it's actually going to go exactly opposite. And then you do usually write these like this, just because it's harder to do it in textbooks top and bottom. Boron has 3, and so 3 electrons as far apart as possible actually make a triangle. So we're going to put them in a triangle shape around boron. And that actually helps us with the shape of the molecule that it makes. We're going to talk about trends here. A couple of trends that you do need to know. So francium, right here, has the largest atomic radius, atomic size. And helium has the smallest. You say, wait a minute, doesn't hydrogen? Well, helium, since it has 2 protons in the nucleus and it's only still on that first shell, those 2 protons actually attract those 2 electrons in tighter than just 1 proton and 1 electron can attract each other. So it does increase from helium down to francium. Okay? If I'm looking at ionization energy, this is the amount of energy that it takes to rip off an electron from an atom. So the ionization energies increase as I'm heading towards fluorine. Actually, they actually increase even more if you head towards helium, because helium is a noble gas. So you try and take off an electron from a noble gas that has a full, stable outer shell, and the ionization energy, or the amount of energy it takes to rip that electron off, it's extremely high. Okay, so we're at the point where it's study for the test. If you haven't understood anything, please come and see me and study hard. Don't be stupid. I see you did well in school, but what real-world skills do you have? Tests. I can make tests and take tests. We need to make sure you understand it, so make sure you come in and get help.